Hello students, welcome to this lecture on digital electronics and microprocessors. In this session, we shall discuss about the analog to digital converters, the digital to analog conversion techniques, and also about shift registers. These three topics are necessary for you to hold a good grip on the subject of memories, because these form a part of the memories also. In sequential circuits also they are very widely used. So, we shall begin with these data converters. As part of the analog to digital and digital to analog conversion, we shall discuss about the need for analog to digital and digital to analog conversion, the D2A conversion techniques using R2R ladder network, and how the analog to digital conversion is performed using successive approximation method. The first question arises as if why we require the analog to digital conversion and also the digital to analog conversion. It is necessary because in general the equipment we used will consist of both analog as well as digital signals. Out of this, due to the advantages possessed by the digital and analog signals individually, we prefer some measurements in those parameters only, but at times it will be necessary for us to convert one form of the data to another form. One of those is the measurement in digital form is easier. Students, most of the times in your laboratory work, you should have observed that the measurement of voltages, currents and many other parameters will be easier when we use the digital multimeters and so. When we use the analog multimeters, sometimes we face the problem of parallax error in arriving at the fine measurement, and also at times we may not be able to measure the value on the given scale. So, we may have to go for scaling of the given parameter. So, by observing these, what we find is that the digital multimeters are useful for us, they are more user friendly. So, we find that the measurement in digital form is easier, because most of the physical quantities are analog in nature, but measuring these quantities in digital form is easier than in analog form. These physical quantities may be temperature, heat, voltages, currents and many more. So, the digital form measurement is easier, hence we convert these analog signals to digital form and then measure them in the digital form. Therefore, the analog to digital conversion is required. The second most important aspect is the storage of these values. Suppose that you have measured certain parameter, but you want to store it for future use. When it is in the analog form, the storage will have to be done by making use of capacitors and so. But in long run, these capacitors will leak away the charge possessed by them, and hence the value contained will decrease. Moreover, the analog signals will have instantaneous values. The storage of these instantaneous values is very difficult. Moreover, if they are at higher frequencies, then it is not very easy for us to follow these changes in the instantaneous values. Hence, for storage purpose, we go for the digital signals. If an analog quantity is stored, its value may come down with time, whereas in digital form, we can use the memory cells, the ROM, RAM and all. The memory systems that we have discussed previously will be useful to store these digital data. Hence, to store a given value that should not change with time, we go for the digital form of the values. This is the necessity for analog to digital conversion. As an example, we shall see. Here you can find a telephone signal connected to a computer. Most of the times you should have seen the internet connection at your laboratories. How the wire is coming to the computer. The telephone line is terminated in a device called as modem. What does it do? It converts the analog signals coming over the telephone line into the digital form on which the computer works. So, here in this example you can find that this telephone contains analog signals. Those signals are converted into the digital form by using this analog to digital converter. Those digital signals will be processed by this digital computer. Then why a digital to analog conversion is required? Once the computer performs the required process on the values, the user requires the processed values. Hence, to get back those processed values in their original analog form, we require a back converter, that is the digital to analog converter. So, to get back a quantity processed or stored by the digital system, a digital to analog conversion is required. See here, suppose that some sound or a talk was stored previously in a computer. Now, if we want to listen it through this loudspeaker, which is giving output in the analog form of sound, we require a digital to analog converter. You should have listened to songs, MP3 songs through these. So, the digital form is converted into analog form of currents. Those are fed to the voice coils of the speaker, and this speaker generates the sound. So, to get back the value stored or processed by a computer, we require a digital to analog converter. We shall see how these digital to analog conversion techniques are performed. As though there are many number of circuits designed to perform these, the most efficient one of these is the R2R ladder network. Hence, we shall see that R2R ladder network form of conversion from digital values into analog values. Here you can see an R2R ladder network. Why the name R2R ladder is given is, you can observe that the arms in this, say the series arms, are of value R, and those in shunt form are 2R. Here, through these input terminals D3, D2, D1, D0, we are going to feed the digital bits. Across this resistor, we get the output. Here VA stands for the analog voltage. So, here nodes are formed at various places. You can see here this is one node, another node as such. Now, based on certain specific properties contained by this R2R ladder network, this will work more efficiently than many others. You can see that the impedance to the right of a node is 2R here. This is the node, and to its right the value is 2R. This is the specific property which we shall observe at each node. For this node, you can see here this is 2R, and if you are going to ground this will be connected to ground, and that comes in parallel to 2R. The resultant value of two equal values put in shunt is nothing but half the individual value. So, the overall value is R only. Once these two R's are put in series, the equivalent value is 2R. You can observe that once again to the right of this node the resistance is 2R only. So, the impedance to the right of a node is 2R again. Similar will be the case if you are observing the network reduction, if you apply the network reduction techniques and observe the impedance at other nodes, say here and here also, the impedance to the right of this node will be 2R. That is the property of a ladder network. The property is that the impedance to the right of a node is 2R. Now, we shall see how this conversion is made. As though these are of equal value, for the output being taken at this resistance, we are going to show it a little of different color, but for that it is equal to others in value. Now, see, if a given digital value is applied to this, supposing that only the MSB bit is 1. So, here starting from D0 to D3, D0 is the least significant bit and D3 is the most significant bit. If only D3 is high and others are low, then what will be the analog output value VA? That we shall see. From our previous discussion, what we discussed is that the impedance to the right of a node is 2R. Hence, to this right of this node, the impedance is going to be 2R. Now, if you place these in a little systematic manner, you can see the arrangement here is same as this 2R and this 2R placed like this, and a digital value of V equivalent to logic 1. Suppose that some 10 volts or 15 volts of V is applied. If this is the potential divider arrangement, what voltage do you expect at this analog value VA? It must be half of this, because these two are equal resistors over which this voltage will be divided. Hence, the analog value will be equal to V by 2 if MSB, if the most significant bit is 1. Hence, if MSB in this case it is D3 is high, then the analog value will be half the value assigned for the digital high. So, VA is equal to V by 2. Then we come to the next bit. If the D2 bit only is high, what will be the value of analog voltage? In this case again, once again we apply the same concept, that to the right of a node the impedance is 2R. This is the data. To the right of this node the impedance is 2R. The D3 is made low, whereas D2 only is high. To the right of these other bits D1 and D0 are low and they are reduced to show you that to the right of this the impedance is 2R. For this network arrangement, the equivalent value of VA can be calculated by putting this in a little more systematic manner. See here, this is the 2R value, here 2R is grounded. So, here it comes like this. So, R 2R, then 2R and 2R. So, 2R, 2R, R and 2R. The voltage across this orange resistance is considered to be the analog output voltage VA. Now, when we apply the network equivalents, the series impedance of these two results in 3R, and when the voltage is divided between these by applying the potential division rules, we find that the voltage across this will be 3V by 8. The same will be the voltage across this resistance 3R. Since 3R is nothing but a series combination of R and 2R, the voltage across these two put together is 3V by 8. But is it the voltage that we require? No. Only the voltage across this 2R resistance is the analog voltage. Hence, out of this 3V by 8, what is the amount dropped across this? It is going to be V by 4. Once again, if you apply the potential division rules, you find that the voltage across this resistor or the analog voltage will be equal to V by 4. That is, if D2 is 1, VA is equal to V by 4. Similarly, you can find the analog voltages when only D1 is 1 and the rest are zeros, and also when D0 only is 1 and the others are equal to 0. When you apply that concept, we find that the analog voltage when D1 alone is high will be equal to V by 8, and when only D0 is high and others are 0, the analog voltage will be equal to V by 16. So, when only one bit is made high and others are made low, we get different values of the analog voltage. Then we apply an important rule on these concepts to build the R2R ladder network. First, we summarize all these. When D3 alone is high, it is analog voltage V by 2, it is V by 4, V by 8 and V by 16 if the other bits are high. When more than one bit is 1 at any time, in general, in practicality, you do not apply only single bit as high value. In general, we apply a word that consists of many ones and zeros. Hence, we shall see the practical problem. What happens when more than one number of bit is high? This R2R ladder network is linear in nature. Hence, you can apply the superposition theorem to it. What the superposition theorem states? The total output voltage is the sum of the output voltages due to individual inputs. That is, you can calculate the output voltage for individual bits, add them together and find the output voltage as equivalent to the required analog voltage. We shall see the same with an example. For a digital input of 1010 and a logic high level of 16 volts, what is going to be the analog output? Here 1010 is the input. As per the superposition theorem, the analog voltage will be equal to the analog voltage due to D3 only and also analog voltage due to D1 only. So, when you put these two together, it will be V by 2 plus V by 8, it is going to be 5V by 8 volts. You can see here, due to D3 alone it is going to be V by 2 and due to D1 alone it is going to be V by 8, and hence put together V by 2 plus V by 8, it gives the total output voltage as 5 V by 8 volts. In the second case, when the digital input is 0, 1, 1, 1, how do you think will be the output? The analog output voltage will be equal to the sum of the outputs due to D2, D1 and D0. So, here due to D2 it is V by 4, due to D1 V by 8 and due to D0 it is V by 16. So, put together the output voltage will be equal to 7 V by 16 volts. This is how we calculate the analog output voltage for a given digital input. We summarize the values here. 5 V by 8 is equal to 5 by 8 into V is the analog digital equivalent logic high value, it is equal to 16. So, 10 volts. In general 1010 in hex form. For your easiness in calculation, I have taken this example. 1010 refers to 10 volts. Similarly, 0111 refers to 7 volts. So, if this is the input, you are getting analog output. If this is the input, the equivalent analog output is 7 volts. Then, how this R2R ladder network will be useful for us? Since this has only two values of resistors R and 2R, building this network is easier. Moreover, if it does not result in loading problem. Loading in the sense, if there are multiple values of resistors, a higher value of resistor will get lesser current and it tries to draw more current through a lesser value of resistance. That is avoided by choosing uniformly only two values of resistors. Moreover, you can extend the ladder network to any number of bits. If you have a 16-bit digital input and want to convert it into analog form, it is very easy because only form R and 2R as such put in a ladder form, you can extend the digital word to any extent. That is another important advantage of this R2R ladder network. So, students, till now we have seen the digital to analog conversion techniques. Now, we shall see the analog to digital conversion techniques. This is the block diagram for the analog to digital conversion. Here you can see a digital to analog converter put inside this, a register called as successive approximation register and a comparator, usually an operational amplifier. The required analog input is fed to this one input of the comparator. It is compared with the DTA converter output. See, the counter consists of the digital data and that is taken as the digital output. This digital value is converted into analog form and compared with the input value. Based on the result, we make changes in this digital value. Starting from MSB most significant bit, we keep on changing one bit at a time of this counter value. So, once it ends at the least significant bit, that will be the equivalent digital value for the given analog input. This is how a successive approximation type of analog to digital conversion is performed. See here, how we perform this is first reset this counter to zeros. Once all zeros are fed, we start the conversion. The analog input is given and at first upon giving this analog input, the MSB of the counter is made to 1. You can see it is made from all zeros to MSB set to 1. Then this digital value is converted into an analog equivalent value by the digital to analog converter. So, send this value into the digital to analog converter and it converts this digital value into analog value and gives an output value VE. Suppose that this is the digital value analog value required. What you do next is this analog equivalent is compared with the analog input value Vi. This is the actual input that we have given, this is the equivalent value of the digital value. These two are compared, whether this is high or this is high. The comparator takes the decision and then based on the value which one is greater, we have to proceed differently. Suppose if Vi is lesser than Ve, it means that we will have to decrease the counter value in order to come closer to the analog value. So, if Vi is less than Ve, we will have to reduce this. How? If Vi is less than Ve, the MSB of the counter is reset to 0. So, make this 0 and then next significant bit is set to 1. This is made 1 and proceed the conversion. So, if this is higher, that is Vi is lesser than Ve, what happens is make this 0 and this into 1, then proceed, that is convert this digital value into analog value. The other way, if the input value is higher than the equivalent value, what you will have to do? You will have to increase the counter value. So, the MSB is not changed and the next significant bit is set to 1. So, this should be set to 1, this should remain 1. So, this is both these two bits are made ones. As such, this process repeats until you reach the LSB. Once the LSB is also changed, the value available will be treated as the digital equivalent of the required of the given analog value. This we shall check with an example. If the input voltage is 13 volts and a 4-bit successive approximation register is used, what should be the equivalent digital value? At first, the analog input value is 5 volts and you set the MSB to 1. So, 1 and others are set equal to 0. It is converted, sent to the D to A converter and then the equivalent analog value is available. It is equal to 8, 1 0 0 0 equal to 8. So, we have two values now. For the comparator, there are two values available, the input value as 5 volts and the equivalent value as 8 volts. So, what it should do? Take a decision, which one is higher? It finds that the input value Vi is less than the equivalent value Ve. Then what should take place? When Vi is less than Ve, we have seen previously that if Vi is less than Ve, the MSB should be set equal to 0 and the next significant bit must be made high. That is what we have to do here, right. So, here you will have to reset this D3 which is the MSB and then made to 0 and then make next significant bit which is D2 is to be set, that is change it from 0 to 1. Upon making this change, you have to proceed normally, that is send this value and find the analog equivalent value. At this time 0 1 0 0 is equal to 4 volts. Now, the comparator should compare these values and take a decision. So, input is 5 volts, the equivalent value is 4 volts. So, in this particular case the input voltage is higher than VE. So, what should be done at this stage? Once again I recall what we have seen when Vi is greater than VE. If Vi is greater than VE, the MSB is not changed, whereas the next significant bit should also be set to 1. So, see here, if Vi is greater than VE, no change in D2. So, keep 0 as it is and make this as, keep 1 as it is and set this value of D1. So, 1 and 1. This is the digital value. Send it to the digital to analog converter, find the equivalent value. It is now equal to 6 volts. Now, comparator should compare 5 volts of input voltage, 6 volts of analog voltage, and once again the input voltage is lesser than VE. Now, once again what should happen? This should be reset and the next bit should be set. Then send this into the DTA converter, find the value. It is equal to 0, 1, 0, 1. Compare these values, input value, equivalent value. These two values have become equal. Now, in this process we have reached the LSB, so we should stop the conversion technique. So, the data contained in this converter should be treated as the equivalent digital value. So, the value equal to 5 volts is 0101. That is, the required digital output is 0101. This is how we get it as the digital output. Students, till now we have seen the data conversion techniques, but also we have to see the shift registers, which are another important parts of these sequential circuits. So, we shall see the shift registers. As part of these shift registers, we shall study the need for a register, how the data transfer from one register to another will take place, and also see the working of the serial in parallel out, parallel in serial out, shift left and shift right type of registers. At the end, we shall see how the shift register will be useful as memory. At first, we shall see the types of shift registers. Based on the direction of shift, they are either shift left registers or shift right registers. What do you mean by a shift left register? If the input data is moving from LSB towards the MSB, then that will be called as shift left register. Here you can see D0, D1 as such. D0 is the LSB and D3 is the MSB. Data is moving from input to output from LSB towards the MSB. This is how the data moves. Upon each clock pulse, one data bit will move inside. In contrast, from MSB to LSB, the movement results in the shift right register. What do you mean by the serial data input? It means for every clock pulse that you give, input will be one bit of input will come and enter into the flip flop. If this is the input, then upon each clock pulse, one bit moves into the register. On the third clock pulse, third bit moves, and on the fourth clock pulse, the fourth bit has moved. This is the serial data input, whereas the opposite will be the serial data output. On the first clock pulse, the first bit has come out. On the second clock pulse, another bit on the third clock pulse, as such. that is the serial data output. The last bit has also come out. Now, what do you mean by parallel data input? At once, the data bits will be fed to all individual flip-flops, that is the parallel data input. On the strike of this clock pulse, all the data bits will enter into the respective flip-flops. Similarly, the parallel data output refers to emergence of the outputs simultaneously from various flip-flops at the stroke of the clock pulse. So, here once the clock pulse is made high, all data bits will move out simultaneously, that is the parallel data output. Based on all these, we shall see the working of the serial in parallel out shift register. It has a clock pulse and a clear signal. For example, we take a 4-bit register that requires 4 flip-flops. At first, the clear pulse is given that makes the content of all these flip-flops to be 0. At a later time, the input is given to the first register, that is the serial input is given from this flip-flop, and parallelly the output is available at all the flip-flops. When the clear pulse is given, the content of all the flip-flops becomes 0. The same is available at the output of each flip-flop, and now the input bits are ready to be fed into the last flip-flop. So, upon each clock pulse, there should be transfer of data bits from one flip-flop into another. We shall see that dividing the entire process into different clock pulses. On the first clock pulse, the first data bit will arrive. So, this is the first data bit serially fed into this flip-flop, and upon the clock pulse feed, that will be stored and the same is available as the output at this flip-flop. When the clock goes low, that will be available as the input for the next flip-flop. It is also ready as the output bit. On the second clock pulse, this input will be given, this bit will be given as input to the second flip-flop, whereas a new data bit is ready to be fed to the first flip-flop. So, 1 0 is the input, 0 1 for the second flip-flop. Upon the clock pulse, what happens? Simultaneously, this data bit will be stored in this flip-flop and 1 will be stored in the second, and the same bits will be available at the respective outputs of the flip-flops. They are available to the next flip-flops as inputs and also at the output lines. On the third clock pulse, these were the input bits ready to be fed into the respective flip-flops, and this is the content stored in the individual flip-flops. On the clock pulse, these input bits will be stored in the flip-flops, and also simultaneously the same outputs will be available at the flip-flops. So, one is stored in this flip-flop and hence it is the output. Similar is the case with other flip-flops. The same will be fed to the next flip-flop as input and also available at the output bits. On the fourth clock pulse, another bit is available at the input, and the previous bits have moved as input bits to the next flip-flops. What happens on the fourth clock pulse? These bits will be stored in the flip-flops and hence their content changes along with their outputs. So, the output available upon completion of the fourth clock pulse is 1010. Then once we feel that 4 clock pulses are over, it is time for us to take out the output. For this, we give an output enable signal to all the flip flops simultaneously. At once the output will move, that is available to be taken out. So, this is how the output is taken out by us once the output enable signal is given. That was how we have fed the data bits serially and obtained the output in parallel form. We have seen that for each clock pulse, one serial bit was fed to the LSB flip flop, and the output was taken only once all the 4 clock pulses were fed and only upon making the output enable signal high. That was the serial in parallel out shift register. Students, now we shall see another type of the shift register, that is the parallel in serial out shift register. This is the shift register consisting of 4 flip flops. The data bits are parallelly simultaneously available for feeding. Here we have a shift load complement signal that is useful to shift the content or load the individual data bits. At first, we make load bar is equal to 0 so that we can load the digital value. Parallel bits can be loaded. Once this is made 0, parallelly what happens? Simultaneously, this being an inverter, at these points the logic value is high. Hence, these are the AND gates with one input as 1, whereas with this being 0 and given to the AND gates, the AND gates shown in black will be disabled because one of the input is 0, whereas these AND gates have one of the inputs as high. Now, we load the input signals. Since these are 0, these individual outputs will be 0, and once we feed the input signal, the input data bits are fed simultaneously at these 4 AND gate inputs. You can see they are available at this flip flop, at the output of this AND. Since this one of the bits is 1, 1 0 made it 0, 1 1 made it 1, 1 0 made it 0 as such, and they are available as inputs for these flip flops. Then upon loading, it is now time to shift these contents. So, to make shift by load bar is equal to 1. Simultaneously, all these are inverted and become 0. So, these AND gates 1, 2 and 3 become disabled. Whereas, other AND gates receive the input from the individual D flip flops. At first, this flip flop, on the first clock pulse, the content will be moved to the right. See here, on the strike of the first clock pulse, this D flip flop stores the input and the same is available as the output at those individual flip flops, and that is carried on to the AND gate, and the AND gate will send the same through the individual OR gates into the next flip flops as inputs. So, at the end of the first clock pulse, the data bit 1 has moved to this place, whereas others have moved by 1 bit to the right. Due to the second clock pulse, the similar thing happens. This data bit still remains to be 1 and the same is sent as input to this flip flop, whereas the previous inputs will be stored in the flip flops and they are made available to the AND gate. So, 1 is available, 0 and 0. You can see that data bits are serially coming out. The previous data bit was 0 and now the data bit 1 has come out of this register. Similarly, the AND gate will send this input through the OR gate to the next flip-flop as input. On the third clock pulse, you can see that the data bit 1 is contained in this and others are contained in this. On a similar basis, these data bits are stored and their outputs are sent to the AND gates. These AND gates will send them in turn through the OR gate, whereas the last output has sent the last bit into the serial fashion out. Similarly, through the OR gate sent to the next flip-flop as input. Upon the fourth clock pulse, a similar procedure takes place and you can see that data bit 1 has come out. This is how we are performing the parallel to serial conversion. You must have remembered that the data we have fed simultaneously was 1 0 1 0 and at 1 bit at a rate time we have received the serial data as 1 0 1 0. This is how we get the parallel to serial conversion. So students, that was the lecture on A to D converters, D to A converters and shift registers. You should have a good knowledge in these registers and data converters. They will be very useful for you in the microprocessors. So I hope that you got good knowledge about these. Thank you all.